ladies and gentlemen. This is Alice from Beijing, and I'm so happy to have you here this Friday for iCANX Talks. As you know that we have these talks every Friday. We connect the world and universe by high tech, the online talks from the whole world. So this week we're going to have a very interesting topic for the advanced manufacturing. Actually, everyone knows that manufacturing is the most important things in our real life and for the societies. So this week we're going to talk about what's happening now and what's really useful for the future, these manufacturing technologies. And this week we have two speakers. One from China is Huang Yongan, was from the best mechanical school, was Huazhong University of Science and Technology, and he's a young professor, but he really done a beautiful work and a very useful work. We have another speaker, was Jay Guo, was from University of Michigan and Ann Arbor. So he's a very famous professor in manufacturing field and done many interesting work. And today is going to talk about something new, how to use a light for the fabrications. And I'm so glad to tell everyone that my best partner, Paul Weiss, is here with us. He's going to introduce our second speaker and he's going to host the panel discussions. Without further ado, let's have our first, speakers, Yongan Huang here. As I say that Professor Huang was from Huazhong University of Science and Technology. He's one of the best young scientists at his age. He won a lot of words. I couldn't, read all the list. That will take more than 10 or 20 minutes. And he has very rich experience in the manufacturing. Now, today is going to talk about the story for the enabling design and manufacturing for the flexible hybrid electronics. So, Yongan, floor is yours. Stage is yours. Please go ahead.
Alice, thank you for introducing me. It's my honor to give a talk here. I would like to share my research work about the enabling design and manufacturing for flexible hybrid electronics. We all know that the flexible electronics come from microelectronics, but different from microelectronics. Flexible electronics exhibit some special features such as small thickness, large area, high accuracy, and strong stretchability. They overturn the physical form of the microelectronics, can integrate with objects with complex surface. They have important applications in flexible display, healthcare, skin of the robot, and the smart skin of the aircraft, and so on. They are bringing about the electronic technology revolution. One of the most important issues is to propose suitable design and the manufacturing method for the flexible electronics. Flexible hybrid electronics are usually made of different materials that may be organic materials, inorganic materials, and nanomaterials, and different structures that are rigid, flexible, even stretchable, and different devices that are thin or thick, small or large, and finally for different applications. So the studies include four important aside: material, design, process, and applications. The site has a large span from the nanoscale materials to micro-scale structures and to macro-scale devices. Today, we discuss the design and the fabrication of micro-scale structures. This talk consisted of two parts: enabling design and enabling manufacturing. First, I would like to share the structural design, electrode design, and integration design. Secondly, I share the studies of multifunctional EHD printing for various applications. The left figure is a typical flexible hybrid electronics that are fabricated by my group. Before design, we need to know what are needed to be included in design. First of all, the mechanical design has to be adjusted, including the stretchability of system, the conformability on rigid and soft curved surface, and the stability under pressure and stretching. They are all critical for the flexible in organic electronics. Secondly, we have to take specific electrical design for large area flexible electronics, including anti-interference to improve the single to nodal ratio. Finally, how to integrate various kinds function or various devices together is critical for multifunctional devices. It's a primary task and a big challenge for stretchable electronics to achieve large stretchability without significant sacrificing the electrical performance and the area coverage. Iceland bridge structures are widely adopted in stretchable electronics. The bridge is designed for highly stretchable interconnector and the Iceland for rugged chips. Various kinds of interconnects have been carefully designed. The most effective geometry are wave-shaped structure, serpentine structure, and self-similar structure. High stretchability can provide a bigger design space for the rugged chips. Self-similar structure can highly increase the stretchability. This kind of structures have been utilized in stretchable electronics. However, it's challenging to analyze the structure properties theoretically. Usually, the geometric shapes are totally different. Meanwhile, the factile order are also different from 1 to 2 to 3 and much bigger. It's challenging to establish a model for these self-similar structures. Here, we establish a recursion equation. Based on it, you don't worry how many orders in the self-similar structure. Once the geometric parameter of the first order structure are given, you can establish the model for the self-similar structure with any order and reduction ratio. The elastic stiffness of the fractile interconnects is determined analytically. The middle figure indicates the relationship between the stiffness and the orders. The normalized tensile stiffness decreases with the orders number. The tensile stiffness is clearly expressed by a set of non-dimensional parameters. We fabricate a two-order self-similar structure, and it can be stretched up to 400%. The structure in the previous page is freestanding. However, it's a big challenge for this kind of structure to be encapsulated. In practice, the self-similar interconnects bonded with the elastomer substrate is more common. It's difficult to model this kind of system theoretically, so we utilize a scale law to establish the mechanical model to predict the stretchability. Firstly, we suppose the max strain is like the equation 1, including two parts, one for out of plane, another for in-plane strain. The parameter eta is the height to width ratio, and the reduction ratio beta is the size ratio of the large structure to the small structure. Secondly, the effect for the out plane and the in-plane buckling with the geometric parameter WL1, W divided by L1, T divided by L1 are computed by finite element method, and the result shows that the maximum strain is linearly proportional to these two parts. So one can get the scale law equation like the equation 2. Thirdly, in the same way, we can get the first part of maximum stretch Fe is linear proportional to the square of the external strain, and the second part is linear proportional to the square root of the external applied strain. So we can get the scale law like the third equation. Finally, we let the maximum equal to the yield strength. One can get the stretchability like the fourth equation. So we can predict the stretchability. When the structure design is finished, you may think everything is done. In fact, the problems are just the beginning. For example, the 7-time structure exhibits high stretchability, but appear unstable buckling and stretching and compressing. The easy appear wrinkle like this one, buckling, delamination, leading the failure of the electronics. At the same time, the sudden instability put a huge influence on the precision of flexible sensors. In stretchable electronics, buckling of microstructure and pressure is inevitable. There exists out-of-plane buckling and in-plane buckling. Although exists a study of a critical understanding for the buckling behavior, including the critical strain for buckling and the wavelength and the amplitude of buckled structures. The left two figures show two kinds of buckling, like the out-of-plane buckling and the in-plane buckling. What inherent control the competition between the two buckling modes? The simplest method is to calculate the systematic energy of the fiber on substrate structure. Then one can get the critical strain of the two buckling modes, respectively. Now, we can establish a criterion to judge which buckling mode appears. The criterion is equal to the ratio of the two critical strains. When it's larger than 1, out-of-plane buckling appears. Otherwise, the in-plane buckling appears. Theoretical analysis and numerical simulation discover that the ratio of head to waist is a critical factor to control the buckling competition. The right figure presents the influence of the cross-section of the structure on buckling mode. The insert figures are the FEA, finite element analysis result of the buckling at the case of the aspect ratio equal to 0.7, 0.6, and 0.3. So it's significant help to fabricate since the buckling is mainly determined by the cross-section rather than the material. This is very useful in manufacturing. On the other hand, 7-time structure will also buckle and stretching. We can observe from the left figure that the thickness determined by the deformation mode. The sink bar geometrics are used to replace the thin ribbon layout to yield open mode deformation instead of merely buckled mode. It is more suitable for high stretchable electronics. In the middle box, the 3 regions of deformation occurs in this range: wrinkling, buckling, and scissoring. The scissoring is stable deformation. The thinner the structure are, the easier the wrinkle is. And the thinner the structure are, the easier the source is. The moderate thickness is easy for buckling behavior. The right figure shows that the force displacement curve with the ratio. With the increase in the structure, the in-plane bending behavior suddenly changing to the out of in-plane buckling to out of buckling. The 2 lines is the solid line, the dashed line. The unstable changing point for the structure with different thickness to width ratio is calculated theoretically. Another question is conformability. Conformability is mechanical adaptivity that can attach to curved surface in a manner that is mechanically invisible to the underneath object. The conformal design is complex and interesting. The electronic device may be thin or thick, rigid, flexible, or stretchable. The objective surface may be developable, non-developable, rigid, or soft. Sometimes even the flexible electronics show high stretchability. They must be still difficult to conform on curved surface because of the rigid island. Comprehensive mechanical understanding of the conformability can offer important insights and racial guidance to the design of flexible electronics. Okay, the left figure is the schematics of epidermal electronics on soft skin. We adopt energy method to establish an interfacial mechanical model to describe this system. The total energy includes bending energy, membrane energy, skin energy, and the adhesion energy. Then one can get the total energy smaller than 1 as the case of conformal contact. A criterion can be established to judge the conformability. The middle figure gives the effect of thickness of the device. One can get the conformal condition. Certainly, the total energy is related with both the thickness and the elastic modulus of the device. The results are plotted in the right figure. One can conclude that epidermal electronics with low bending stiffness, smooth and soft skin, strong adhesion, promote the conformability. Compared with the soft surface, the hard surface don't accommodate any elastic energy, making the electronics much easier to generate wrinkle and delamination. The left figure is the conformability of Iceland bridging structure on a rigid, non-developed surface. The right figure shows the maximum strain in Iceland with non-dimensional wires during conformable contact. The conformability depends on the wires of Iceland. We also obtain the final critical wires as shown in the red formula. Notably, it's very different between the stiff and the soft surface. The conformability of stiff surface depends on the width of the devices, but that of the soft surface mainly depends on the thickness of the device. The large area unstretchable electronics can conform on complex surface via kirigami technology. However, the traditional kirigami cannot avoid the out-of-plane buckling. Bio-inspired soft art design opens a path for the application of kirigami mechanical metamaterials in flexible electronics. We present a soft hard material based on kirigami technology, which avoids the out-of-plane buckling. Additionally, if the soft material are conductive, one can build functional circuit. We build a display based on the metal materials on various surfaces and a dynamic surface. From the small one to the big one is a dynamic surface. Besides the structural design, the electrical design is also very important to improve the signal to noise ratio. Electrophysiological activities are ubiquitous and spatial temporally varying on the human skin. Large-scale collection of biopollution benefit for digital healthcare and human-machine interactions. The multi-electrodes covered the For arm, the area is very large, so it can gather more information. Meanwhile, the interference of epidermal interconnects can no longer be overlooked. In order to enhance the signal-to-noise ratio, electrical compensation is needed. Traditionally, the lamp parameter model is adopted to get the biopotential. It is merely suitable for the traditional small gel electrode. Because of the small area, the assumption of uniform potential is valid. However, it cannot be used for large area flexible electrode, since the biopotential is not uniform, and the interconnector also gather the biopotential along it. It will lead to significant disturbance. So we divided one whole model into distributed parameter model, like the right figure. The equation is like this. The distributed parameter model accounts for the area of the electrode and the interconnect, as well as the skin and the muscle covered by them. The electrode in the right frame is general one without compensation part. The length of the electrode is L1 plus L2. So this is a total electrode. One can get the electrode potential V1 based on the distributed parameter mode. It can be noted that the final potential contains the effect of part 1, contain the part 1 potential. So like this one. In order to reduce the effect of the part L1, the simplest method is to adopt another part that is the same with part L1 and put it along with part L1, like this one, compensation branch, the blue one. We call it compensation branch, the blue one. So one can get the partial compensation mode. It's equal to V1 minus Vc. It's a little pity that the two dominator is totally different. So one cannot completely remove the effect of part L1. In order to realize the fully compensation, one method is to make the dominates in the red box are equal. Make the two dominates equal. So we can make the box equal to 0. Then one can get the compensating impedance C. The compensation part is made up of two parts. Compensation branch, like this one, branch, and the compensation electrode. The former is similar with the partial compensated model, and the latter is utilized for the impedance C. Suppose that the skin is uniform, one can get V3. One can get the V3 just from the blue box. Based on this equation, one can get the electrode, the voltage of the electrode just here. From this, we can find that the length of the compensation electrode is the same with the work electrode. The compensation electrode is connected with the ground. To validate this single compensation theory, we carried out a careful design experiment. As illustrated in the figure, the design electrodes are equal length in this experiment. In experiment, we take the ECG as the single, owing to its obvious features such as the PQRST like this one, and take EMG as noisy. The EMG is much smaller than the ECG. Our prime objective was to qualify and then eliminate the effect of EMG on ECG using this strategy. There are 4 channels. Channel 1 acquires the reference, namely pure ECG. And the channel 2 acquires the ECG plus EMG. And the third one, switch off. When the switch off, here, switch off, we can CH3 and CH4 get the partial compensation signals. When the switch on, channel 3 and the channel 4 get the fully compensation signals. All the 4 channel simultaneous work. These are the experimental results as shown in the right 4 figures. Without external disturbance, namely without EMG, all the electrode can get excellent work result. However, when the EMG sync are introduced as external disturbance, the green result, namely the partially compensated method, don't work well. And the right bottom figure shows the fully compensated model do work well. The compensated ECG remain as clear as the pure ECG, despite the EMG disturbance. The result successfully validate our compensation strategy. In addition to the ECG, EMG, the Electro can work as a multifunctional sensors, including measuring the hydration, body temperature, and respiration. We do an experiment. The object drink hot water. Therefore, the body temperature increased first. And then the hydration of the skin also increased. Additionally, the electrode can get the ECG signals. When enough signals are required, one can get respiration behavior from the amplitude change. Like this one is dedicated the respiration. The large area electrode is able to be, the large area electrode is able to be utilized in human-machine interactions. The video shows this. The video shows the Fabricate numeral directly in Chinese gesture. The EMG signals are captured by the Electro and recognized by computer. The right figure gives the signals of grabbing something with different strengths. The feature of the signals is very clean, which is greatly helpful for recognition. American Sign Language is the predominant sign language used in the deaf communities in the United States and Canada. Hence, recognizing ASL via EMG is a benefit for the deaf to interact with computers and robots. 16-channel EMG signals on the forearm was recorded using the Electro. The upper figure shows the classification accuracy of the 26 alphabet and the rest gesture after verification, except this one, S. Other gesture can classify with very high accuracy. The average classification accuracy is as higher as 97%. The lower accuracy for the S may be attributed to the similarity with other alphabets, such as the A, E, M, N, which could be improved by increasing more channels. Real-time ASL recognition through EMG was demonstrated by participants continuously expressed hello, HELLO, is work continuously. The large EMG electrode can also serve for the disabled. The left-hand amputee, thus wore a 16-channel Electro, could repeatedly control a robot processes to express his intentions, such as rest, grasp, and yes, and so on. The ability to continuously measure subtle change in pressure using devices mounted on the skin is valuable for monitoring vital signs in emergency care. In order to find out your blood pressure, the cuff inflates to a point where it temporarily cuts off the blood flow, and only basic pressure values are given, just the high pressure and the low pressure. The devices are still too big for daily life and cause discomfort during long-term use. Flexible sensors is an excellent candidate for blood pressure monitoring. In our work, the piezoelectric film are adopted and bonded to the gate electrode of TFT. The systems are very small, lightweight, thin, and capable of stretching to conform to the skin, while providing high level of pressure sensitivity, quick response, and excellent fatigue properties. A schematic illustration of a thin, comfortable piezoelectric pressure sensor illustration of these devices, which include a square area of piezoelectric thin film transducer based on PZT, the green one. Each PZT film is encapsulated above and below with PI film, the brown one. All these pedals are interconnected by gold layer. They're supported by a silicon substrate, the blue one. The gold layer connects to the gate of TFT by a stretchable 7-tie trace. The source and the drain terminals of the transistor serve as the external output of the sensor. The right is the cross-section of schematic illustration of pressure sensor and its connection to an associated transistor. The right one is the equivalent circuit for capacitance coupling between the pressure sensor and the transistor. Firstly, the piezoelectric response is critical for the pressure sensor. The dependence of the voltage of the PZT on applied pressure is different from PZT sensors on rigid silicon wafer and on a soft silicon substrate. It's rigid silicon, is soft silicon. The two different substrates. The PZT device on the silicon substrate offer a response that about more than 2 order magnitude greater than those of identical device on the silicon wafer. So the soft substrate, the bigger the output. It results from the deformation of PZT array. The FEA, the finite element analysis result, shows there exists a scale factor of 6 order between the mounted on the silicon and the silicon substrate. Under the right figures exhibit the output signal increase with the applied pressure and the vice PDMS. More importantly, the effect of loading position from this left to middle and the right is also very critical for practice application. One can observe that the output of signal is sensitive, is not sensitive to the loading position. It's needed to stick the sensor more easily on the skin. I will show you how to establish an electrical model to combine the PZT sensor and the TFT together. Firstly, we discussed the PZT, how to model the PZT. This is the Piezoelectric Equation, standard equation. Here, we suppose the electric displacement is equal to 0. One can get the strain at a function of electric field strength E. Then submit the strain into the first equation one can get the electric field strength as a function of pressure P. We know that the electric field strength E multiplied by the thickness of Pzt equals to the voltage, like this one. The strength multiplied by the thickness of Pzt is equal to the output voltage. From the function, we can find that it's determined by the thickness of the Pzt and the area of the Pzt and the applied and the piezoelectric constants and the contact area and the loading applied loading. Oh, the modular of the gate bias with applied pressure is related with the Pzt. From the left bottom figure, one can find that the output figure with output voltage is just several microvolts, which is about 6 order magnitude smaller than the input voltage of the TFT. However, in experiment, such small voltage is still able to drive TFT. Why? It takes us a very long time to address this problem. Well, there are two tandem capacitors, the same charge between the two capacitors. The magnitude factor equal to the ratio of the capacitor. We can get two total different voltage between the two capacitors. Based on the capacitor equation, we can calculate the Pzt capacitance is equal to this one. It's a microfarad. The next issue is how to calculate the capacitance of the gate electrode part of the TFT. The TFT is a multi-layer thin film structure, and there are 3 dielectric layers, and the capacitance can be calculated like this equation. The material and the thickness of each layer are listed in the table, including the size, thickness, and the dielectric constants. Then one can get the capacitance of TFT. From the TFT with channel wise 200 micrometer, the capacitance we can get is like this one, it's PF. And the 800 micrometer wise one is like this one. So we can get the ratio between the two capacitors. The two capacitors, one is Pzt, another is the TFT. So we get the ratio is about this one. From this, it makes the driver about 10 to 6 power. It will make the drive voltage is about 7 volts. Okay, so far the TFT does not still combine with the Pzt sensor. We need to measure the output of TFT to characterize the whole system output. This is the standard equation of the transistor. It contains 2 quark states, saturated state and the non-saturated state. Usually the saturated state is used as a switch. Here, the non-saturated state is used to establish a single amplifier and a filter. The TFT is in the working range in our devices. Based on the equation, one can easily get the change of the drain source current IDS that is related to the change of driving voltage, as shown in the bottom equations. Okay, after a series of modeling, including the piezoelectricity model, the capacitance model, and the transistor model, one can get the whole model for the integration of Pzt sensor and the TFT, as shown in the bottom equations. From the point of the modeling, we finish the whole integration design. It provides a way for the modeling of integration of various devices. Okay, the flexible sensor is attached onto the wrist. Change in IDS is a result from the various in pressure associated with blood flow. The completely pulse pressure waveform is known to provide valuable information for diagnostic and therapy of various diseases. The blood vessel examined here affect about 20 Pdt elements in the array. The peak level of P1 is the systolic pressure, and the P2 is the diastolic pressure. And very important, we can measure the diastolic tail information. The device, such feature provide additional detailed information. However, they are unable detachable with conventional methods. Therefore, normalized average IDS collected once per week for a month. It is suitable for a long-term pressure wave monitoring. Okay, after discussion of design of flexible electronics, I will share the progress on the manufacturing of flexible electronics. I just focus on electro hydrodynamic printing, in short, EHD printing. Okay, there are two kinds of flexible electronics, which are organic electronics and inorganic electronics. The former can be fabricated through the solution-based process, such as inkjet printing and screen printing. It's a high efficient, cost-effective manufacturing. And the latter one is compatible with the traditional micro fabrication technologies. It is used for high-performance flexible electronics. One of the key steps is to delaminate the flexible electronics from the rigid substrate. So in this part, I just introduced EHD printing to organic electrodes. Okay, usually the traditional inkjet printing fabricates structures in a job-on-demand manner. The printed structure usually have zigzag edge, so they are not suitable for stretchable electronics. At the same time, there is a strict limit of the ink for traditional inkjet printing. The viscosity is merely from the 5 to 20 CPS. The resolution is larger than 20 micrometers. However, for EHD printing, a higher voltage in electric field is applied between the nozzle and the substrate. The applied voltage can polarize the solution at the tip of the nozzle and pour the ink from the Taylor column. EHD printing pulls the fluids out of the nozzle rather than push them. The EHD printing deposits structure in a job-on-demand manner, like the traditional inkjet printing, or a continuous manner. The resolution is smaller than 1 micrometer, that is about 2 orders higher than the traditional inkjet printing. And the viscosity is from 1 to 10,000 CPS, about 3 orders larger than that of traditional inkjet printing. There are three kinds of force in the jetting. There are three kinds of force in the jetting process, including the electric field force, the surface tension, and the viscous force. Based on the relationship between this force, one can get 3 printing modes, such as the EHD jet printing that works in a job-on-demand manner, and the EHD direct writing that works in a continuous manner, and the electro spring that deposits film directly. EHD jet printing is usually adopted to fabricate micro and nanostructure array. It has been adopted to fabricate the flexible display, including the pixel layer, anti-reflection layer, and so on. EHD direct writing can fabricate straight or wave-shaped smooth structure, so they are suitable for interconnect wires, stretchable electronics, transparent metal mesh, and so on. And the electro spring form nanoscale film on two-dimensional planar and three-dimensional curved substrates. Okay, it is still hard journey to merely print a job. There are 4 important issues that have to be addressed, including the jetting frequency and the volume during the generation, the jet breakup during flying, the bubble captured during the deposition, and the coffee ring during the drying. As shown in the top left figure, one can adopt high-order resonance to improve the jet frequency and the volume. Certainly, the frequency and the volume are also related with the viscosity of the solution, the diameter of the nozzle, and the strength of the electrical field. And as shown in the top right figure, the flying jet had a high density of charge. When the charge density exceeds a critical value, the jet may be break up into 2 jobs or more satellite jobs. These jobs are harmful in printing. When a job deposits on a substrate as shown in the bottom left figure, it is easy to contain an air bubble in the center. It's also harmful for printing. When the electrical field applied, the charge will gather at the 2 ends of the jobs when the charging job is close to the substrate. So the telecom will form at the bottom end. It's helpful to drive air bubble out of the center. Finally, beautiful liquid jobs without satellite jobs, without air bubble, silent lie on the substrate. In his mind, it just want to become a solid state and keep the appearance at the same time. However, usually since always a big fire, coffee ring is ubiquitous in printing, and it is also inevitable in printing. It is a result from the solute gathering at the edge of the dot. Reducing solute movement rate can reduce the coffee ring. One of the effective ways is to increase the viscosity. However, it makes inkjet printing more difficult, even makes the nozzle clogged. So it's seldom to be used in traditional inkjet printing, but it's totally different in EHD printing. Here, a perovskite solution is adopted in inkjet printing for display, and PVP is a special material in the precursor ink. The main role is to increase the viscosity of the ink. Okay, the different PVP concentration adopted, which have various viscosities from 10 to 600 CPS. It can be observed from the right figures that the coffee ring is effectively suppressed, like this one. It can be observed from the top left figure that the dots without any coffee ring are formed. Furthermore, the large-scale dot array with various material, size, and shape are fabricated, and the diameter is smaller than 1 micrometer. In the right figure, various full color patterns are fabricated. The solution of the full color pixel are perovskite. It is potential for high resolution flexible display. In addition to the display, it can also be utilized to fabricate full color photo detector. The image is shown as the left top figure. Each pixel contains 3 sub-pixels, red, blue, and green. The featured size is 2 micrometer, and the resolution reaches about 700 ppi. The photo detector becomes flexible when it is stripped from the glass substrate via laser lift-off. An experiment is carried out as shown in the right bottom figure. A mask of a host is adopted. The red light passes through the letters H and S, and the green light passes through the letter U, and the blue light passes through the letter T, and the detector can clearly show the color, shape, and strength of the light spots. In addition to the 2D pattern, it also can be used to fabricate the optical supersurface, which is made up of 3D microstructures. The left image is an OLED display. The luminescent layer is located at the middle layer. The light will be reflected back by the interface or surface of the transparent electrode layers and the substrate. In order to reach the expected brightness, one has to increase the power. The super surface is an effective way to improve the anti-reflection. The EHD printing can generate high viscosity UV-Q solution, and the high aspect ratio dots can be gotten. However, the duty ratio is very low, like this one. The anti-reflection effect is limited. One of the most tasks is increase the duty ratio. Hydrophobic pattern is adopted to form the fine mesh. The pattern is fabricated by EHD direct writing process that we'll discuss in the next page. We will precisely control the shape of the lens. Then we use the EHD jet printing to form the lens job by job. We can precisely control the aspect ratio. The duty ratio can reach as high as 99%. Finally, the light transmittance is improved with 40%. Let's discuss the second printing mode, namely near field EHD direct writing. Usually the jet flight like the left figure. It shows significant unstable behavior. We call it whipping effect. How to control the whipping is a question of questions. There are 2 ways. One is sharply reduce the distance between the nozzle and the substrate. The main reason is that the jetting in such short distance is not accelerated adequately. There exists a stable segment. The velocity is slow, so the jet is stable. Another method is to utilize the high-speed motion stretch to join the jetting to make the whipping jet stable. It's very similar with the Chinese kite that is drawn by a person. The EHD direct writing is also determined by the solution. There are 2 kinds of high viscosity solution. One is like a silver paste that is broken easily. Another is like honey, such as a polymer solution, which is difficult to be broken. For the paste, one can only use the stable segment to write pattern. However, for the honey-like solution, one can use both the stable segment and the high-speed motion stage to directly write pattern. And at the same time, the high-speed motion stage can further reduce the diameter of the jetting and easy to reach sub-micrometer, such as 2 nanometer. Another important feature is control the cross-section shape from the cycle. This is cycle fiber to the thin film by adjusting the distance between the nozzle and the substrate. It's well known to us the traditional printed circuit board, in short PCB, is fabricated by etching. Instead of printing, it leads great environmental pollution. The EHD direct writing is adopted to deposit paste to fabricate a large area flexible PCB. There exist different kinds of pattern, including fine conductive interconnector and and the large area pens. The digital printing is suitable for customized products and small-scale production. More important, the smooth structure are critical for flexible electronics. Of course, EHD printing can deposit the photoresist to form pattern. That is a necessary step in traditional photolithography process. The left figure exhibits the standard photolithography process, including 8 steps. It needs a physical mask and alignment, exposure, and developing. It is meaningful to utilize the EHD printing to replace the 4 steps to form the same resolution photoresist pattern, just one step. The pattern is directly generated by computer. EHD lithography is a short flower process and can reduce 3 steps. Finally, the resolution of EHD lithography is higher enough. It can reach about 100 nanometer, much higher than the conventional mask alloy in university lab, whose resolution is about 1 micrometer. Now let's show how to use the method to fabricate a flexible TFT. Just 3 steps are needed in pattern the electrode. The mask is printed directly, followed by spatter coating and a thin film. Then, removing the mask, one can get the pattern film. The resolution reached as small as 1 micrometer, so that a small channel length is generated for TFT. This method can replace the mask layer. More important, it can work on curved surface. A flexible TFT array can be fabricated and that shows significant transistor performance. In previous page, the place that is covered by the printed photoresist needs to be removed. Inversely, in this page, the place that is not covered by the printed photoresist needs to be removed. For example, we use this method to fabricate a transparent metal mesh for flexible touch skin. Firstly, the substrate is coated by thin metal film, and then the mask is printed on the film via EHD direct writing. Thirdly, the object is put into etching solution. Finally, we removed the photoresist. We get the metal mesh film. It can act as a touch screen. As shown in the left figure, the transparency is very high. Additionally, we can also fabricate an ultra-thin transparent layer. It can fully conform on a fingerprint, act as a fingertip mouse. We know that serpentine structure is critical for stretchable electronics. How to fabricate the microstructure is very important and it's meaningful, as shown in the figure. When the jet touches the static substrate, it becomes unstable, and rotates. It's interesting to utilize the rotation to fabricate the serpentine structures. Now let's discover the mechanism of the pattern transformation. related with the viscosity of the substrate. In the geometrical model, the deposited trace on the collector become your 5 kinds of structures. It's related with the velocity ratio. V is the velocity of the substrate. UC is the velocity of jetting at the contact point. We established the equation to give the pattern theoretically. Meanwhile, the critical value for the transformation of the patterns are given. Now I show how to fabricate serpentine structure and the self-similar structures. So it's a very long process. Firstly, you have to fabricate the serpentine structure and then put it on a stretchable, a pre-strain the substrate. When release the substrate, the serpentine structure will buckling, and you have to control the buckling direction. And another question is how to make the global buckling, not the local buckling, is another important question. Finally, we can get the self-similar structures. Based on this kind of structure, we fabricate piezoelectric sensors. We use the PVDF piezoelectric materials. This sensor is very sensitive. It's a very small gain. We get that about 205 milligram. Okay, the next process is here is simply discuss the electro spray process to show application in deposition of thin film. The left two figures show the process principle of the electro spring. The higher voltage drives the jet to overcome the relay limit and the charge drops formed. When overmuch charge in the drops that will split more and much smaller drops, we utilize it to deposit thin film. The right video is the equipment in the working state. The equipment is developed by our group. And the fabrication of MEMS, such as the crystal oscillator, is difficult coating uniform the photoresist on the top and the lateral surface. The left figure shows the photoresist film deposited by this process. It's very uniform, and at the same time, the lateral surface is also coated by the photoresist film. And very important, the flexible display habit high deformability, so it's difficult to be encapsulated by glass sheet like the traditional display. The flexible display is usually encapsulated by organic or an inorganic matter layer. The thin film encapsulation replaced the glass in flexible display. Printing for organic layer with thickness of 2 to 4 micrometer, and the uniform is about 3%. In addition to the photoresist UV cured solution, resin, nano-silver, and perovskite graphene can also be electrosprayed into thin film. Based on the design and the manufacturing, typical flexible hybrid electronics are fabricated. This system contains flexible substrate, rigid chips, flexible sensors, large-scale conductive lines, and so on. We adopted the plasma process, EHD printing, and so on. And all the equipment of this process is developed by my group. This system is used as the flexible smart sensing scheme of aircraft to measure the physical parameters such as the pressure, strain, temperature, flow speed. One can get the aerodynamic parameter, including separate point, transition point, lift force, and so on. In the last part, I would like to share the equipment that we developed for flexible electronics. We developed the various kind of EHD printer for the patterning of the flexible electronics. It had high resolution and high compatibility with various ink. Additionally, we developed an industrial equipment for printed display. It had been integrated to the test production line of printed display. Micro manufacture fabrication technology can be used to fabricate flexible electronics. The last step is to delaminate the thin film electronics from the substrate to make them flexible. This is a laser lift-off equipment for striping of flexible electronics from rigid glass substrate. To make the electronic flexible, we can fabricate 1 micrometer thin flexible electronics. This equipment combines the laser lift-off, transfer printing, and EHD printing, as well as the machine vision, laser measurement systems, and so on. It focuses on the fabrication of curved electronics. Finally, this is the research planning of my group, including design, manufacturing, and applications. In the side of manufacturing, in addition to the EHD printing, we are studying the laser lift-off, plasma etching, and mass transfer printing, and so on. Especially the application include smart skin of aircraft, e-skin of robots, epidemic electronics for healthcare, and flexible display. Finally, we welcome young research to join my group. This is my WeChat. You can add me as a friend. My group has 3 excellent levels for materials, design, and the fabrications of flexible electronics, respectively. That's all. Thank you for so long attention. Thank you very much.
Okay, so Yong, what a nice talk, and so many information, very rich, your lab, and all this equipment looks very nice. Now there are a few questions was come out. Yeah, actually before the question come out, I may ask the first questions to you. As for the equipment you mentioned in the last few slides, so can the university buy that? Is that affordable? The price is okay for the university lab?
Thank you. I think that is a very good question and a good advisement. All this equipment are fabricated by our group, and some of which are sold. For example, the EHD printing, we have sold about 20 and 30 about equipment every year. And most of the sold to the university. University, yeah. Some and big industry, some equipment integrated with the industrial lines.
Okay, I see. Because I was hosting a conference, in the States. I saw many exhibitors. They go there and they discuss with, customer from institution and the universities. And then many of university asking for this kind of fabrication tools. So I suggest next time you go to join the conference. Okay, that's why my question. Let's go to the questions from the audience. Yeah, so the first question is quite simple. For the electrode on the skin, I think is in the very beginning part of your talk. What kind of glue you use for the adhesion? I think you have some trick on that. Is it normal glue or something?
Oh, okay. I think it's a very good question. In the tattoo, don't need any glue in practice. You just need the water. You just put water on the forearm and then put the tattoo on directly.
So simple. I put some water down here and then put your chip on that.
Yeah. It's very simple. But another question is very difficult to stripe it from the skin.
Okay.
but sometimes in you can use the water is doesn't work at all. The students in my group give a very interesting method. Just use the I don't know how to present it. 化妆棉.
Okay, I see. The ladies.
Ladies water. Ladies,
Yeah.
especially water for ladies to make up. Yeah.
Okay, I see that. So, yeah, it's out of my mind. You just use water and it can, for a few days or week like that.
Yeah. Last month, my student do an experiment. He the tattoo used much more than a week. In the last day, he put 7 on his face, just one broken, just one broken. Because there is no substrate, he is breathable. Is no substrate on the tattoo. So and very thin is about just 1 micrometer thin. So it can attach the stick on the skin very easily.
Okay, I dream that it don't feel any comfortable because it's just 1 micron. The thickness is so thin. Yeah.
Yeah.
Should be like later I can put some down here, make me look so much more, beautiful.
Yeah. It's determined by the patterns.
I see. Thank you very much. It's so a very good answer for the questions. The next question is for the EEG and the EMG detection. How about the long-term stability and compare with the traditional measurement?
How about the long stability compared with the traditional measurement? Okay, I think this because the tattoo is very thin, so you can just stick it on your skin and then connect with wireless devices such as the Bluetooth. You can go anywhere you want, but the traditional measurement, the gel electrode is very thin. So you maybe you can wearable, but you can do a stronger movement because it's very thin and it's very the heavy. The weight is very heavy. So they introduce many noise to the signals. So it's very difficult for the traditional gel electrode for long-term stable. Thank you.
Okay, this one better. Okay, the next one for the blood pressure detectors by PZT and TFT. I realize that you do not need the air inflation pump. It is a big progress. Can you compare the results and the long-term stability with the light-based BP detector and the traditional BP meters? How about its power consumption? So for the blood pressure.
Yeah, it's a very good question for practical applications. Yes, the cancel the inflation purpose because it's just put on the skin sometimes. But another question is, I have to say, the sensor just to give the pressure one person to one person. Different person have different skin, and for the older man different from the young man. The men different from the women. Yeah. So the total difference is a big engineering problem. So then you have to stable a big deep base to collect all the different all kinds of signals from different people. This is one question. Another one,
I will compare with other, detectors, the meters for the blood pressure. So normally they use a bulky one, someone use like this was a light, light base.
Like this watch is sometimes it's very difficult to to wear anytime because it's large, it's very large, and because it needs the inflation pump. This is traditional BP meters. But in watch, such as the Huawei watch or Apple watch, okay, it's very difficult to get the pressure directly. At least currently, it's very difficult to catch the pressure. But in my group, I have studying this sensors with Huawei cooperations. Okay.
Very good. Okay, it can use a pretty long time for you sensor, right? Because the last question is, yeah, for the power consumption. So it's pretty low.
Yeah. But because it's just in the lab, I don't think about the power consumption at all currently.
Okay, I see. Looking forward, that is very useful for many peoples. Okay, we have the next question is Professor Huang. E-jet printing is a powerful tool for large scale manufacturing. How about process temperature and can it print different materials easily?
Okay. I thank you very much. So good questions. The process temperature is just in room temperature. It's okay. But sometimes if you inkjet printing of the melt solution, you have to increase the temperature of the noodle. For the usually the solution or ink is just in the room temperature is okay, and it can be printed different materials easily, but the material solution is totally different, especially the viscosity from the very low viscosity like the water and to very high viscosity like the honey. All can be printed by the EHD printing.
Wow, it's also can print honey. What a good story. We can make a Charlie chocolate, factory.
Yes.
Okay.
And the
Good.
resolution is very high. Okay.
Okay. The last question is exciting talk. As you said in your slides, it can be printed on the cover surface, covered surface. How to control the alignment of multiple layers and the resolution it can achieve. Does it has any limitations?
Oh, okay. It's a very difficult question for multi-layers in curved surface. In my lab, we used the 5-axial motion stage, but the precision is about 30 micrometers. It's just about 30 micrometers. Because it's very easy for the planar substrate to print it, such as the 1 micrometer is very easy. But in the curved surface, I think it's very difficult. But sometimes we use the self-aligned printing, because the structure on the curved surface is higher than the surface. So the electric field is much stronger. So he can absorb the inkjet to his surface. So I think it's very interesting, but it's I'm writing the paper. Maybe
Okay, we will see your paper soon. Thank you very much, Yongan. Very nice talk and wonderful. As a host of iCANX talks as a tradition on this stage, I hand over this e-version of certification for you using your technology, connect the world and universe. Proud of you. Thank you very much.
Thank you.
Yeah. Now it's time for we go to the panel discussion, and I welcome Jay and Paul Weiss get on the stage. Paul, is your time, please? Yeah. So please, yeah.
Yes, thank you so much, Alice, and welcome, Jay. We thought we'd talk about manufacturing today, and maybe let's start by Jay, you've looked at many different technologies, I think some of which are sort of ready to move towards industry and others sort of further upstream. Can you talk about the difficulty of translating from a university laboratory into a manufacturing scenario, and maybe what the differences in accessible tools are for you and your research group versus what they'll see after they leave your group and head to a company?
Okay, Jay.
Okay, that's a long question. Can we break it into several parts?
Sure.
Yes.
So the first part, I think you are asking about, what we do in the lab, how is it transition when it's transitioned to, real world manufacturing? What are the challenges? Is that correct? Or
Yes.
okay, yeah. My experience is that from laboratory discovery, right, to making small samples and then be able to scale it. For example, you might make multiple samples, get a consistent behavior, right? This is just the beginning step, right? And then when I really try to apply this technology, any technology, to the real world, right? There are many more requirements that we researchers are not necessarily even aware of. Yeah. So for instance, Professor Huang talked about some of their work. I'll also touch on this transparent conductor work. Yeah. So we thought, several years ago, well, okay, we demonstrated, okay, this very conducting, transparent, it's flexible, and so on. We thought our job is done, right? But then when actually we start to talk to, let's say, quote unquote, potential customers, right? The first question asked is that, okay, can your sample satisfy the requirement of surviving in a high temperature, high humidity environment for several hundred years, several hundred hours, right? So these are sort of questions we don't even think about when we do our research. Yeah. So I think in my view, writing scientific papers, right, is easier than pushing a technology to the real world. That is a far more difficult task and very challenging.
Mhm. And maybe let's go over to Yongan.
Okay.
This
Okay.
beautiful work, and touched on things like registration and so forth that are issues when one gets to manufacturing. Maybe you can also comment on the gaps between what we do in the research lab versus getting over to manufacturing.
Okay, okay. I just take an example for the printer. I started printing 10 years ago. 10 years ago. I'm very young. I just postdoc.
Yeah, how old are you?
Focus on the printing about the 2008 year. 2008. I started the study of the printing. Because I'm very young, just at that time, I just writing paper. I think how to get how to improve the precision and improve the capacities with the materials and so on. But at that time, it's okay for me just writing paper because I can become associated professor just by papers. But when you become associated professor, the paper is no longer meets the requirement. So I have to change the paper into product. So I have established a group, the group including the engineers and the students and me together, work together. So I have to develop the equipment, but sometimes it's so difficult because you have to develop the experimental platform first. You can use you can realize the mechanism of the printing. Then you have to develop a prototype machine and then put the machine into the pilot patent test. So it's very, very long. Another important, you have to need enough money to develop the machine. So it's very expensive for any machine. So so maybe sometimes if you have good and big the research plant, you have no research project, and you have no money, you don't get the machine. And finally, okay, that's all.
Then I think that's a very good point. The scale, even of cost of manufacturing is so great in industry that it's hard for universities to match up in some sense. And I mean, one of the things that I think we enjoy is our alumni coming back and saying what's different about their jobs when they're making chips at or other devices at Intel, AM, or Apple, or somewhere else.
Okay, Paul. Can I ask a question for you? It's related to this. Yeah. So
yeah,
I think many years ago, you are very famous for making the IBM, the atom, that manufacturing, right? You make that one. The pattern looks very pretty. About this was kind of the world leading work, and how about the later? Is it technology, transfer to the foundry or something? Yeah, how it does that in IBM this way? Yeah.
Well, okay. So actually, the Don Eigler, who I worked with, learned to spell after I left IBM. I was just trying to find out what was underneath the atoms that we were imaging when we first moved atoms around. But that wasn't really targeted towards manufacturing, much more towards scientific demonstrations. But the development of the scanning tunneling microscope itself was really put together to look at holes in oxide surfaces. That's what Binig and Rohrer and Gerber were after when they developed the instrument. So there was a real purpose, scientific, or I should say engineering manufacturing purpose to that tool. It's just it opened up the nanoscience world to us, very similarly for transistors, right? There was the need to have amplifiers for relaying signals from AT&T, what was the telephone company at the time. And so Bell Laboratories pushed semiconductor technologies forward with a real intent to, change how communications worked in terms of hardware. And so I think the two feed off each other. And, that's what's kind of interesting about doing research directly into manufacturing for me is how one does that, but moves the field forward at the same time that the industrial competition, if you will, for both the Yongan and Jay, is at least funded 1,000 times better.
But that's a big sign, your work really enriches the world. They say that it's possible to move even down to the atom level, that one. Yeah, so it's great. So I mentioned that, but Yongan and Jay, and even me, you don't know that I was graduated from the mechanical school.
Mhm.
I got my degree was where Yongan was now. Yeah, is working there, HUST, Huazhong University of Science and Technology. I was getting my PhD from mechanical engineer. So all the things was bulky, Yeah, well, I was studying everything if you touch about the manufacturing. So everything was a bulky machine, oil looks nasty, something like that, So when we saw your paper that time, we're excited. Wow, we make so kind of fantastic things. Yeah, just give a big kind of pressure on that. So I follow that questions. I may ask this. So Jay and Yongan, both of you are in very traditional manufacturing department. right? Mechanical department and your school or department are famous for this. Now you guys move on to the advanced manufacturing. It looks like now Yongan things with thin film, soft electronics. Jay, you will use light source to do all these things. How is this transfer from a traditional bulky oil one to all this like fancy one? Okay, we'll go first. Maybe Jay, you'll go first. Yes, senior.
Okay, sure. I'd be happy to. Just one little correction. I'm actually now working in a sort of manufacturing focused department myself. I'm with the electrical engineering. The mechanical engineering here in Michigan, yes, they have a major division in manufacturing, and they're actually talking about forming a advanced manufacturing institute. Yeah. So my background was, let's say, from PhD level. It's actually in microelectronics. Yeah. So I was primarily working on very tiny transistors that actually make use of what you call quantum effect or single electron effect. So you have to make things really, really tiny. Yeah. But that's for scientific sort of study. Yeah. But after I joined Michigan, I started to sort of turn my interest in photonics. First of all, because they are relatively larger, right? So they are easier to make, and the effect is much easier to observe, right? Rather than have to cool down to below liquid helium temperature to observe something. This, in fact, you can do things at ambient room temperature. Yeah. But we start to make devices. However, I always, since I joined engineering, I always have a desire to not only demonstrate something, but to also to show people that they can actually be practically made. So not only I can make it, other people can follow and can make it as well, right? The real success from engineering perspective is really to push it to the real world application rather than just publishing papers, right? So that's why I have always asked and pushed my students to not be satisfied with what they get, okay, but think further, right? How to push this further, yeah. So that's my
Okay, very good. So Yong'an, how about you?
Okay, I think this is a long-term problems for any university because you have to become stronger and stronger. But sometimes the traditional manufacturing is also very important. But in our school, usually the older teacher focus on the traditional manufacturing, and the school absorbs new teacher from all over the world and focus on the new focus on innovation. And sometimes in another opinion, the big group focus on the traditional manufacturing. So sometimes in traditional manufacturing, many difficult. So you have to absorb a big group to do this work. Sometimes in new innovation, they just need a new idea first. So the new teacher can do this. After 5 or 10 years, the new teacher become the older teacher. He can make get a big group, so he can do the traditional machine, because at that time the new technology become traditional technology. This is my opinion. Okay.
Okay. Paul, please.
Yes. So, I mean, one of the ways that we, I would say, add some realism to what we do is we hire faculty in from industry. And so those, both the faculty and students who've spent some time in industry really inform, what we do. And it's sort of the equivalent to biological control experiments. I think you both talked about being thoughtful in terms of putting together experiments and using your creativity to develop tools that could be useful in manufacturing. And so maybe you can tell the students and postdocs out there from where you get that, those insights. Maybe we'll start with Jay.
Let me see. I may not completely get the question.
So what I was saying was, when we hope that, as leaders of research groups and parts of collaborations, that we are, taking into account the realism of, what it would really take to get to manufacturing at an industrial scale. And so where do you get, do you get collaborators? Do you get from visits to industry, from, students who've gone on? Where do you get the insight that you need to provide that for your group? And with students or postdocs out there, how should they try to approach those problems?
Okay, I got it. Sorry. For me, yeah, sure. The students and postdocs, these are very good resources. In fact, let's say manufacturing, right? What Professor Huang described and what I want to talk about. You can see that it's actually generally multidisciplinary. You're not just solving one particular problem. So it involves so many different aspects. So therefore, having students with the right background to be able to handle those are very important. So even though I'm in electrical engineering, computer science department, but I'm very lucky to have the opportunity to work with students from multiple disciplines. For example, mechanical engineering, right? Macromolecular science engineering. So those are students who know more about polymers than I do, right? And applied physics. So these students all bring their own expertise and insight. Yeah. So that's very helpful. One of the technology that I will touch on first is related to patterning, right? To bring this nano imprint to a scaled up, continuous high throughput process. Yeah. So in this case, it's a roll-to-roll nano imprint. I mean, this idea has been out there for a long time, right? I thought about it a long time too, but how to realize it? Yeah, it's only when we have certain materials developed, okay, that actually is suitable for that process. Right? That's condition number one. And number two, I think is far more important, is the person, right? Yeah, I happen to have a right person coming at the right time, and I give him the task. Yeah, and actually it didn't take too long, yeah, for him to come up with a prototype. And he's from mechanical engineering. Yeah, thinking back, if I, let's say, ask a traditional electrical engineering student, it might be a very difficult task. Yeah, it might easily spend, I don't know, a good 2 or 3 years to figure out a solution. So I think, bringing people expertise from diverse background, right, is very helpful. Yeah, and also have visit to industry, right, to see what they are doing. That's extremely helpful. Yeah, if the industry are open to you. Okay. Yeah. And sometimes, of course, when you visit a company, they have to take all your phone, all the cameras, so you cannot. However, you can talk to them, right, to get some sense, right? Yeah. This is also very helpful. For instance, when we work on the structural color, which is another topic I will talk about, right? In the beginning, we focus on our interest. That's more, I would say, scientifically interesting, right? You can publish papers and so on, right? And we have ways to potentially mass produce them too. Yeah. But then later on, I get an opportunity, in fact, I get a sponsored project from industry. And they ask us to go back to very simple strategy, just deposit layers and so on. So I was wondering, why do they bother, doing that, right? We're talking about making very advanced structure. But later on, I understand through more interaction with them, and I kind of briefly mentioned in the talk that there is actually great advantage for doing that because it's very scalable, and the industry have already developed certain processes that we researchers in the academic simply don't know. Yeah, so we should learn from these people. Yeah, that's another point. Maybe I'll stop here and hear what Professor Huang has to say.
Yes. So,
Great.
Yongan.
Okay. I think it is a long issue for the teacher to think about how to help the student to work well. In our university, there are two kinds of projects for students. One for the academy students, one for engineering students. In the first one, for the academic students, you have to tell them how to do research about the innovation, and how to write papers and how to get the frontier of the mechanical engineering. But for the engineering student, you can work with the engineering to help the student to work to develop equipment, and they can do the equipment by themselves after they finish the project in the university. And another question is many projects come from the company, because the Huazhong University of Science and Technology is located at the Optics Valley. There are many high-tech companies in Wuhan. So we can combine, because the Huazhong University of Technology, Science and Technology is the highest university in Wuhan. So
In China.
in China. So the high-tech company want to work with our university. So he put a big project to our school and work together. Sometimes just one idea he put to our school, and they can find us a suitable professor to do this project. And when they work for 1 year, 2 years, or 3 years, and they make it become the idea, make it become the product of the company. Sometimes it's determined by lucky. Sometimes you do a lot of research, but sometimes you stay at the lab, only step at the laboratory. Sometimes if you are lucky enough, the company found this equipment, wow, very strong for the maybe to buy it. Sometimes last year I transformed many patent to the company about
30,000?
30 million RMB.
Okay.
I think I'm very lucky last years. Although 2020 in Wuhan is not lucky, but for our university, maybe it's good news.
Okay. As a student or a graduate from Huazhong, I have to add in one sentence here. Yeah, the mechanical engineering school really pushes the students to try to do all these hands-on, experiments started very much. Even I'm a, lady, a girl students, they push that everyone have to do all this kind of hands-on stuff, deal with equipment. So they got good trainings there. Yeah.
Alice, do you have another?
Yeah. Oh, okay. So Paul, I think time is up. We can move to the next. Okay. Yeah.
Oh, very good.
Okay. Yeah. Okay. We move to the Jay's talk. So Paul, you ready? Yeah.
Yes, I am. Yeah.